Settle gently into the quiet of the room and let the day begin to loosen its hold. There is nowhere else you need to be, and nothing here that you must remember. Tonight, we will travel slowly across the sleeping earth, visiting landscapes that science partly understands, yet has not explained in every detail. Our journey begins beneath the pale dawn of the Sahara. In Mauritania, the Richat structure appears from above, like a vast eye drawn into the desert. Its rings spread across the sand for many kilometers, alternating between harder and softer layers of ancient rock. It was once proposed as an impact crater, but geologists now describe it as a deeply eroded geological dome. The broad process is understood, while the exact history of uplift, fracturing, mineral alteration, and erosion remains less certain. Far across the Atlantic, the floor of Racetrack Playa in California lies flat and almost empty. Dark stones rest on the pale mud, each followed by a long trail that seems to record a journey made without witnesses. Researchers have observed thin sheets of ice forming around the rocks after rare winter rain. Light winds can move the floating ice and gently push the stones across wet mud, yet these events are uncommon, and the precise combination of water, ice, wind, and timing varies from one movement to another. From the desert, we can drift southward into a much colder silence. At the edge of Antarctica's Taylor Glacier, a rusty red flow stains the blue-white ice. Blood Falls looks dramatic, but its color comes from iron-rich salty water that turns red when it reaches oxygen at the surface. The brine appears to come from a hidden system beneath the glacier, where microorganisms survive without sunlight. Scientists understand much of the chemistry, but the underground pathways, the age of the trapped water, and the full community of microbes are still being investigated. Under a warmer sky, Lake Natron lies across the dry landscape of northern Tanzania. Its shallow water can become red, pink, or orange, bordered by white mineral crusts and distant volcanic hills. Evaporation and volcanic minerals make the lake extremely alkaline. Salt-loving microorganisms help create its changing colors, while lesser flamingos gather here to breed. Researchers continue to study how water levels, chemistry, food supply, and climate work together to make this severe lake such an important refuge. Our path now crosses the sea toward the isolated island of Socotra. On its rocky plateaus, dragon's blood trees rise like broad green umbrellas. Their shape allows them to collect moisture from mist and shade the ground beneath their branches. Socotra's long isolation has produced plants and animals found nowhere else. Much is known about their adaptation, but scientists are still reconstructing when different species arrived, how they spread across the island, and whether younger trees can survive a future of warmer temperatures, grazing animals, and less predictable rainfall. Across northern South America, Mount Roraima rises above the clouds like an enormous stone table. Its summit holds dark pools, unusual rock formations, thin soils, and plants adapted to a cool, wet world separated from the forest below. The mountain is built mainly from very old sandstone shaped by water and weather. Yet questions remain about the development of its strange summit forms and the history of its isolated species. Some may have survived there for long periods, while others may have arrived more recently than their remote setting suggests. As evening gathers, we move toward Lake Maracaibo in Venezuela. Above the Catatumbo region, lightning can flash repeatedly over distant water and wetlands. Local fishers have watched these storms for generations, using the glow as a familiar presence on the horizon, moist air from the lake, nearby mountains, and shifting winds all help produce the storms. But the strength and seasonal pattern of the lightning can change greatly. Scientists continue to examine how local topography, larger weather systems, water temperatures, and changing climate influence one another. Our next stop lies beneath the ground in Romania. Moval Cave remained sealed from the surface for a very long time. Inside, still pools and damp stones support an ecosystem that does not depend on sunlight in the usual way. Microorganisms use chemicals containing sulfur, methane, and other compounds to produce energy. These microbes support small invertebrates adapted to darkness and low oxygen. Researchers understand the basic food web, but the length of the cave's isolation and the evolutionary history of many of its species remain uncertain. From this enclosed darkness, we return to an open shore. On Kawah Ijen Beach in New Zealand, the Moraki boulders rest on wet sand like enormous stone spheres. Some are smooth and complete, while others have split apart to reveal patterned interiors. They are natural concretions that grew within ancient marine sediment as minerals gathered around small centers. Erosion later released them from the cliffs. Their general origin is well understood, though the exact rate of growth, the formation of their internal cracks, and the differences between individual boulders still invite careful study. Our final stop for tonight's first journey waits beneath the green canopy of the Peruvian Amazon. The Shane Timbishka flows with water hot enough to release clouds of steam into the forest. It is unusually far from the nearest active volcanic centers, which once made its heat difficult to explain. Scientists now think deeply circulating groundwater is heated below the surface before rising along fractures. Even so, the full underground route has not been mapped. The depth of circulation, the sources of the water, and the way heat is concentrated along this river remain open questions. The steam rises slowly between the trees, and the forest becomes quiet again. Beyond it, many more unusual places are waiting beneath distant skies. Leaving the warm mist of the Amazon behind, we travel westward across the ocean, toward a small island off the southern coast of Australia. Lake Hillier appears as a vivid pink oval beside the deep blue sea. A narrow strip of pale sand and dark green vegetation separates the unusual lake from the surrounding ocean. Its color is linked to salt-loving microorganisms and pigments produced in the highly saline water. Yet the exact balance between algae, bacteria, salt concentration, sunlight, and seasonal conditions is still being examined. The lake often remains pink even when water is removed from it. This suggests that the color is not simply a reflection of the sky or the surrounding landscape. Far away, across the dry grasslands of Namibia, another pattern spreads quietly across the ground. The fairy circles are round, bare patches surrounded by taller grass. From above, thousands of them form a repeating pattern across the open landscape, as though the earth has been carefully marked. Two main explanations have received strong scientific support. One focuses on competition between plants for scarce water, while the other emphasizes the activity of underground termites. Both processes may contribute in different places. Researchers continue to debate how vegetation, insects, rainfall, soil, and temperature interact to create circles that can persist for many years. From the dry grasslands, we move toward the clear tropical waters of Belize. The Great Blue Hole is a nearly circular marine sinkhole surrounded by lighter turquoise water. From above, its dark center appears like an opening into a much deeper world. It began as a limestone cave during periods when sea level was lower. As the ocean rose, the cave flooded, and parts of its roof collapsed. The broad history is understood, but its sediments still preserve unanswered questions. Layers of mineral deposits may contain records of ancient storms, droughts, and environmental changes that have not yet been completely reconstructed. Along the coast of Northern Ireland, waves wash against another landscape shaped by very old geological forces. The Giant's Causeway is formed from thousands of dark basalt columns, many with 5 or 6 sides. They fit closely together and descend toward the sea like an enormous natural pavement. The columns formed when thick lava cooled and contracted. Cracks developed as the rock lost heat, creating the repeating polygonal pattern. Scientists understand this cooling process well, but details such as the precise cooling rate and the movement of heat through the ancient lava flow are still studied. Small differences may explain why some columns are unusually large, narrow, curved, or irregular. Our path now turns toward the Danakil Depression in northeastern Ethiopia. At Dalo, shallow pools and mineral terraces glow in shades of yellow, green, orange, and white. Salt, sulfur compounds, hot water, and volcanic gases combine to create one of Earth's most unusual surfaces. The region lies where tectonic plates are slowly pulling apart. Heat from below drives fluids through salt-rich layers before they return to the surface. Researchers continue to investigate whether microorganisms can remain active in its most extreme pools. Some sites may be too acidic, hot, or salty, even for the hardiest known forms of life. From this bright mineral landscape, we descend beneath the sea near the Japanese island of Yonaguni. There, a large sandstone formation rises from the seafloor in terraces, steps, and broad flat surfaces. Its sharp-looking edges have encouraged long debate about whether people once modified parts of it. Many geologists argue that natural fractures, currents, and erosion can produce these shapes. Others suggest that some smaller features may show limited human alteration. No clear evidence has established that the entire structure is an ancient monument. The question remains interesting because natural geology and possible human activity are not always easy to separate beneath moving seawater. Northward, in a quiet valley in Norway, strange lights have been reported for decades. The Hessdalen lights can appear as pale white, yellow, or red glows moving slowly above the valley. Some remain visible for several seconds, while others seem to last longer. Possible explanations include electrical activity involving dust, minerals, ionized gas, and unusual atmospheric conditions. Other sightings may have more ordinary causes, including aircraft, stars, or distant vehicle lights. Instrumented observations have confirmed that some luminous events are real, but no single explanation accounts for every report. The valley continues to be watched with cameras and scientific equipment. Across the Atlantic, a forest stream in Minnesota once seemed to present another quiet puzzle. At Devil's Kettle, part of a waterfall drops into a deep opening in the rock. For many years, Visitors wondered whether the water disappeared into an unknown underground passage. Flow measurements now indicate that the water probably rejoins the river below the falls. The hidden route is likely short and contained within fractured volcanic rock. Even so, the exact shape of the passage cannot be easily seen. The mystery has become smaller, but the concealed movement of water beneath the rock remains difficult to observe directly. Farther north, the frozen ground of Siberia is changing. Large craters have appeared suddenly in the tundra, surrounded by scattered blocks of soil and ice. Some seem to form when gas pressure builds beneath frozen ground and forcefully breaks through the surface. Methane and other gases can collect in pockets as permafrost warms and underground ice changes. Yet scientists are still working to understand why craters form in certain locations and not in others. Many may collapse quickly, fill with water, and become ordinary-looking lakes. This makes it difficult to know how often such events occurred before aircraft and satellites began watching the region. Our final stop lies beneath the forest floor of Mexico's Yucatan Peninsula. Cenotes are water-filled sinkholes connected to an enormous hidden network of limestone caves. Sunlight may enter through openings above, illuminating clear blue water and roots hanging from the forest. Rainwater slowly dissolves the limestone, enlarging fractures into caverns and underground rivers. When a roof becomes unstable, it may collapse and reveal the water below. Divers and researchers have mapped long sections of these systems, but many passages remain unexplored. Their connections, changing water chemistry, ancient sediments, and archaeological remains continue to reveal new pieces of the peninsula's story. The light from the cenote opening grows softer as evening settles above the trees. Beyond the limestone passages, our quiet journey continues toward new deserts, forests, oceans, and frozen lakes. From the hidden rivers of Yucatan, we travel northeast across continents, toward a wide desert beneath the evening sky of Turkmenistan. There, the Darvaza gas crater glows from the surface of the Karakum Desert. At twilight, its orange flames seem brighter against the surrounding blue darkness. The crater began after drilling activity disturbed an underground pocket of natural gas. The ground collapsed, and the escaping gas was set alight in the hope that it would burn away quickly. Instead, the fire continued for decades. The general cause is known, but the underground structure feeding the flames has never been mapped in complete detail. Researchers still ask how much gas remains beneath the crater, how the flow changes over time, and what would happen if the flames were finally extinguished. Leaving the warm desert glow behind, we cross the ocean toward the cold lakes of Patagonia. Along General Carrera Lake, water has carved passages into bands of marble. The walls of the marble caves curve above turquoise water in smooth folds of white, gray, and blue. Wave action slowly dissolved and polished the calcium-rich rock. Changes in lake level allowed the water to work at different heights, producing arches, columns, and hollow chambers. The broad process is clear, but the exact age of individual passages is difficult to determine. Scientists are also studying how glacial melt, lake chemistry, and changing water levels may reshape the caves in the future. Far to the north, in a quiet pine forest in western Poland, another strange pattern appears. The crooked forest contains trees whose trunks bend sharply near the ground before turning upward again. Most of the surrounding pines grow straight, making the curved group especially noticeable. The trees were probably shaped while young, perhaps by human action, heavy snow, damage, or a combination of causes. Yet no surviving record explains exactly what happened. Some people believe the trunks were deliberately trained for curved timber. Others suggest environmental stress. The unusual similarity of the bends keeps the question open. From this gentle forest, we travel south toward the dry limestone country of Madagascar. Chingi de Vimaraha rises like a stone forest, filled with narrow pinnacles, deep cracks, and sharp ridges. From above, the landscape resembles a vast gray maze. Rainwater dissolved the limestone over immense periods of time. Fractures widened into channels, while harder sections remained as blades and towers. Geologists understand the karst process, but the development of such extreme shapes depends on many local details. Rock composition, rainfall, drainage, and the history of uplift all influence the final landscape. Between the stone walls, isolated pockets of soil support plants and animals found nowhere else. Some species may live only within a small group of valleys, separated by cliffs that are difficult to cross. Our journey now turns northwest toward the dry interior of Canada. Spotted Lake changes as summer heat removes its water. Brown mineral pools remain behind, separated by pale ridges of salt and other dissolved substances. Different pools may appear green, yellow, blue, or brown, depending on their mineral content, depth, and the angle of the light. Evaporation explains the basic pattern, but the appearance changes from year to year. Rainfall, temperature, groundwater, and mineral movement all influence the size and color of the spots. For the Silts people, the lake also holds deep cultural importance. Scientific study and traditional knowledge meet here in a landscape that is unusual, fragile, and carefully protected. When darkness falls, we continue south toward the open plains of West Texas, near the town of Marfa. Distant lights have sometimes appeared above the desert horizon. They may glow steadily, divide, fade, or seem to move across the darkness. Many sightings are probably caused by vehicle headlights distorted by distance and layers of warm and cool air. Atmospheric refraction can make ordinary lights appear to float or shift. Yet not every historical report is easy to match with modern traffic. Changes in roads, viewing conditions, and memory make older observations difficult to reconstruct. The mystery may not have one single cause. Different lights seen from the same location may come from different sources. Across the Pacific, a quieter kind of light waits underground in New Zealand. Inside the Waitomo caves, thousands of glowworms shine from the ceiling above dark, still water. Their blue-green light resembles a night sky hidden beneath the earth. The glow is produced by larvae that use bioluminescence to attract small flying insects. Fine silk threads hang below them, forming delicate traps in the cave air. Scientists understand how the light is made, but the brightness and distribution of colonies can vary. Humidity, airflow, food supply, flooding, and the shape of the cave all influence where the glowworms gather. From this living ceiling, we move north toward the winter silence of Siberia. When Lake Baikal freezes, clear ice can reveal stacks of white bubbles trapped below the surface. Many contain methane produced by microorganisms breaking down organic material in the lakebed. The bubbles rise but become sealed beneath growing ice. Their shapes record pauses in freezing, gas release, and changing temperature. Researchers study them because methane is an important greenhouse gas. Yet the amount released from the lake varies greatly across seasons and locations. Baikal is enormous, deep, and geologically active. Understanding how methane moves through its sediments, water, and ice remains a difficult task. We now descend far below the surface of the Gulf of Mexico. On the dark seafloor, dense salty water gathers in brine pools that look like lakes within the ocean. Their edges can be sharply defined against the surrounding sediment. The brine is heavier than ordinary seawater, so it settles into depressions. It may contain very little oxygen and high levels of methane or hydrogen sulfide. Specialized organisms survive around the margins, where chemicals from below support unusual food webs. Scientists continue to study how these communities begin, how long the pools last, and how fluids travel through deep sediments. Our final stop arises beneath a warmer sky in the Philippines. The chocolate hills of Bohol form hundreds of rounded mounds across the green landscape. During the dry season, their grass turns brown, giving the hills their familiar name. They are made largely of limestone, shaped by weathering and erosion. Ancient marine deposits were lifted above sea level, then slowly carved by rain and underground water. The broad explanation is accepted, but the details of their unusually regular shapes remain debated. Soil thickness, drainage patterns, rock structure, and long-term erosion may all have worked together. Morning mist settles between the rounded hills, softening the valleys below. Beyond them, more strange landscapes are waiting. Beneath ice, forest, fire, and distant ocean water. From the rounded hills of Bohol, we travel southward into colder air, toward the broad white silence of Antarctica. Beneath several kilometers of ice lies Lake Vostok, one of the largest known subglacial lakes on Earth. It has remained hidden from sunlight and direct contact with the atmosphere for an immense span of time. Radar and seismic measurements reveal the shape of the water beneath the ice. Scientists think pressure from the glacier and gentle geothermal heat help keep the lake from freezing solid. Yet many details remain uncertain. Researchers still debate how water circulates within the lake, how often it exchanges water with nearby hidden channels, and whether living organisms survive in this dark environment. Studying the lake is difficult because drilling equipment must avoid contaminating it. Even a small sample may contain material carried down from the surface rather than life that truly belongs to the lake. Leaving the deep Antarctic ice, we travel north toward the mountains of Kazakhstan. Lake Kandy formed after a powerful earthquake triggered a landslide in the early 20th century. The falling rock blocked a valley, allowing cold water to rise around a forest of spruce trees. Today, pale trunks stand upright above the lake like the remains of a drowned woodland. Beneath the surface, cold water has preserved branches that would have decayed more quickly in warmer conditions. The lake's origin is well documented, but researchers continue to observe how its underwater forest changes. Water temperature, microorganisms, mineral content, and the slow breakdown of wood all shape its unusual appearance. From the quiet mountain water, we move toward the volcanic highlands of Indonesia. At Kawah Ijen, pale blue flames can appear at night along cracks in the ground. They are not blue lava, but burning sulfur-rich gases escaping from the volcano. The gases emerge at high temperatures and ignite when they meet oxygen. Some sulfur cools into yellow deposits that have long been collected by local workers from the difficult volcanic landscape. Scientists understand the chemistry of the flames, but the volcanic system beneath Ijen remains complex. Gas pressure, magma movement, groundwater, and the extremely acidic crater lake can change in ways that are not always easy to predict. Far across the Pacific, a smaller flame burns behind a waterfall in western New York. At Eternal Flame Falls, water descends over dark shale while a tiny natural flame flickers inside a shallow opening behind it. The fire is fed by gas escaping through fractures in the rock. The gas is largely methane produced within ancient organic-rich shale. Visitors sometimes relight the flame after wind or water puts it out, so the word eternal is more poetic than literal. Researchers have studied why gas reaches the surface here, even though the surrounding rock is not as hot as expected for normal gas formation. The precise chemical and geological history of the seep remains an interesting local question. We now return to Antarctica, this time to the slopes of Mount Erebus, around volcanic openings called fumaroles. Warm gases rise through snow and ice. The vapor freezes in the cold air, gradually building hollow ice towers above the vents. Some towers become tall, twisted, and chimney-like. Warm caves can form beneath them, creating protected pockets where temperature, moisture, and volcanic gases differ sharply from the surrounding surface. Scientists continue to investigate the microorganisms that may inhabit these environments. It can be difficult to determine whether detected life is truly adapted to the caves, or was carried there by wind, equipment, or visiting researchers. From the icy volcano, we descend into the deep Atlantic Ocean. The Lost City hydrothermal field rises from the seafloor as pale towers of carbonate rock. Some are many stories tall, releasing warm alkaline fluids into the dark ocean. Unlike the black smokers found near volcanic ridges, Lost City is powered mainly by reactions between seawater and rocks from Earth's mantle. These reactions produce hydrogen and methane, creating energy that microorganisms can use. The basic process is known as serpentinization, yet scientists are still studying how long the field has been active, how its channels shift, and how similar systems may have influenced the earliest forms of life on Earth. We rise again into daylight over the grasslands of Washington State. The Mima Mounds appear as thousands of rounded earthen hills spread across open prairie. Their regular spacing gives the landscape a carefully arranged appearance. Several explanations have been proposed. Burrowing animals may gradually push soil into mounds, while patterns of water movement, vegetation growth, freezing, and erosion may also contribute. No single idea has explained every mound field in every region. Different landscapes that look similar from above may have formed through different combinations of natural processes. Across the northern forests of Siberia, another circular formation rises from the trees. The Padam crater is a large mound of broken limestone with a raised ring and central hill. Its remote location and unusual shape have encouraged many competing explanations. Most researchers favor a geological origin involving movement beneath the surface, gas release, freezing, or disturbance of deeply fractured rock. An impact explanation has also been considered, but clear evidence for a meteorite has not been found. Its exact age remains uncertain, and the processes that lifted so much rock into a cone are still debated. The forest around it grows quietly while measurements continue. From Siberia, we travel west toward a young island in the North Atlantic. Surtsey rose from the sea during volcanic eruptions that began in 1963. When the eruptions ended, scientists protected the island so they could watch life arrive with very little human disturbance. Seeds reach the black lava by wind, waves, birds, and floating material. Mosses, grasses, insects, and nesting seabirds gradually change the young landscape. Researchers understand many of these arrivals, but ecological development is never perfectly predictable. Chance events, storms, erosion, animal colonies, and soil formation can redirect the island's future. Our final stop lies in the mountains of Utah, beneath a forest of golden leaves. Pando appears to be a grove of separate quaking aspens, but its trunks are connected by one enormous root system. Genetically, much of the forest is a single living organism. New trunks rise from underground roots as older ones die. The clone may have persisted for thousands of years, although its exact age cannot be measured directly. Scientists are now studying why young shoots struggle to survive in parts of the grove. Grazing animals, drought, disease, fire suppression, and climate change may all be involved. The aspen leaves tremble softly in the mountain air, each one moving alone while remaining connected below the soil. Beyond this quiet forest, the sleeping earth still holds many more landscapes shaped by hidden water, ancient stone, and slowly changing life. Leaving the golden aspen forest behind, we travel south toward the high plains of Bolivia, where the horizon becomes almost perfectly flat. Salar de Uyuni is the largest salt flat on Earth. During the dry season, its white surface is divided into vast polygonal patterns that stretch toward distant volcanic mountains. In the rainy season, a thin layer of water can cover the salt. The ground then reflects the sky so clearly that clouds, mountains, and travelers seem to float between two blue worlds. The salt crust formed as ancient lakes repeatedly expanded and disappeared. Beneath it lies mineral-rich brine containing large amounts of lithium, potassium, magnesium, and other dissolved substances. Researchers understand the broad history, but the movement of water beneath the crust is complicated. The thickness of the salt, the depth of the brine, and the rate at which different minerals gather vary across the basin. Far across the continent of Africa, another unusual body of water rests between steep green mountains. Lake Kivu lies along the border of Rwanda and the Democratic Republic of the Congo. Deep beneath its calm surface, enormous quantities of dissolved carbon dioxide and methane remain trapped in the water. The gases enter through volcanic and biological processes. Dense layers of deep water do not mix easily with the warmer surface, allowing the gases to accumulate over long periods. Scientists regularly measure the lake because changes in temperature, volcanic activity, or water circulation could disturb this layering. Methane is also carefully extracted in some areas and used to generate electricity. The general system is understood, but the lake is constantly changing. Researchers continue to investigate how quickly gas is accumulating, how microorganisms produce methane, and how climate may influence the stability of the water layers. From this deep lake, we return to South America and follow a clear river through the forests of Colombia. For part of each year, Caño Cristales becomes filled with bands of red, pink, yellow, green, and dark blue. It is sometimes described as a river of many colors. Much of the red comes from an aquatic plant called Macarenia clavigera. It grows on the rocky riverbed and changes appearance according to sunlight, water depth, and seasonal flow. The river is neither equally colorful throughout the year nor across its entire length. Too much water hides the plants, while too little water can leave them dry and exposed. Scientists understand the source of the colors, but the precise timing and intensity vary. Rainfall, cloud cover, water speed, temperature, and the health of the river ecosystem all help determine what visitors will see. Our journey now moves toward the Atlantic coast of Brazil. Lençóis Maranhenses appears from a distance like an enormous white desert. Yet between its sweeping dunes, thousands of clear blue and green lagoons form during the rainy season. The sand was carried inland by wind from the coast, while rainwater collects in low spaces between the dunes. A layer of less permeable sediment beneath the sand helps slow the water from draining away. Many lagoons disappear during the dry season, but some remain long enough to support fish. How the fish return after isolated pools vanish has inspired several explanations. Some may survive in deeper water or buried mud, while others may enter through temporary connections during floods. The exact answer is likely different from one lagoon to another. From moving dunes, we travel north to a quiet Finnish forest. There, a large boulder called Kummakivi rests on a much smaller stone. The contact point appears so narrow that the upper rock seems almost ready to slide away. Despite its appearance, the boulder is stable and cannot be easily moved. The most likely explanation is that retreating glaciers carried it and left it balanced as the ice melted. Glacial transport is common across Finland, but the exact sequence that placed this particular stone is impossible to reconstruct completely. The shape of the ice, the direction of movement, and the condition of the ground have long since disappeared. The forest has grown around it, turning an ancient geological accident into a quiet part of the landscape. Far to the east, layered hills rise from the dry country of northwestern China. The Zhangye Dangxia landforms display broad stripes of red, orange, yellow, gray, and brown. Their colors come from layers of sandstone and other sediments deposited over millions of years. Tectonic forces lifted and tilted these layers. Wind, rain, freezing, and erosion then carved them into ridges, pillars, and steep valleys. The main geological story is clear, but the landscape continues to change at uneven rates. Small differences in minerals, rock hardness, moisture, and exposure can strongly affect which colors and shapes remain visible. The brightest photographs are often influenced by wet weather, sunlight, camera settings, and image processing. In ordinary light, the hills can appear quieter, with softer bands that shift as clouds pass overhead. Across the Pacific, strange stone towers rise from the shoreline of Mono Lake in California. These pale formations are called tufa towers. They began beneath the water, where calcium-rich freshwater springs met the carbonate-rich water of the lake. The chemical reaction formed calcium carbonate around the springs. Over time, the deposits grew into columns, knobs, and hollow tubes hidden below the surface. When water was diverted away from the lake during the 20th century, the water level fell and exposed many towers to the air. Their full shapes became visible along the shore. Scientists understand how tufa forms, yet the internal pathways of old springs are difficult to trace. Each tower records a slightly different history of water flow, lake level, chemistry, and biological activity. Our final stop lies among 3 volcanic lakes on the Indonesian island of Flores. At the summit of Kelimutu, neighboring crater lakes can display remarkably different colors. At various times, they have appeared turquoise, green, dark brown, red, or nearly black. The colors change as volcanic gases, dissolved minerals, oxygen levels, and the chemistry of the water shift. Iron and other elements can take different chemical forms, altering the way the lakes absorb and reflect light. Researchers can measure many of these ingredients. But sudden color changes are not always easy to predict. The volcanic plumbing beneath the mountain is hidden, and each lake responds differently to gases and rainfall. Clouds now drift slowly across the summit, hiding one crater and then another. As the evening air cools above the colored water, our journey continues toward more quiet places shaped by stone, chemistry, wind, and time. Leaving the colored lakes of Kelimutu, we travel west across the Indian Ocean and the African continent toward the quiet green highlands of Cameroon. Lake Nyos rests inside an old volcanic crater. Its surface can appear calm and ordinary, surrounded by steep slopes, farms, and patches of forest. Deep below, volcanic carbon dioxide slowly enters the lake through groundwater and rock fractures. Because the lower water is cold and dense, it can remain separated from the warmer layers above. This allows dissolved gas to accumulate under pressure. In 1986, a sudden release sent a large cloud of carbon dioxide into the surrounding valleys, leading to a tragic loss of life. Scientists now use pipes to bring gas-rich water gradually toward the surface. Even so, researchers continue to study how rainfall, landslides, temperature changes, and volcanic activity might disturb the lake's delicate layering. From this crater lake, we cross the Atlantic and descend beneath the dry landscape of northern Mexico. The Cave of the Crystals at Naica contains enormous transparent gypsum crystals. Some are longer than a small room and rise from the cave floor at steep angles. They grew while the chamber remained filled with warm, mineral-rich water. For thousands of years, conditions stayed close to the narrow temperature range needed for gypsum crystals to grow very slowly. Mining operations later lowered the groundwater and exposed the chamber. Without its water, the cave became extremely hot and humid, making exploration difficult. Scientists understand the main process, but questions remain about the exact growth rate of the largest crystals and how long the unusually stable conditions lasted. The cave also reminds researchers that some natural wonders only become visible because human activity changes the surrounding environment. We rise again into daylight and continue toward the pale terraces of western Turkey. At Pamukkale, warm spring water flows down a hillside and leaves behind bright white layers of travertine. Shallow pools gather along the terraces, reflecting the sky in soft shades of blue. The water carries dissolved calcium from underground limestone. When it reaches the surface, pressure and temperature change, allowing carbon dioxide to escape and calcium carbonate to settle. This process is well understood, but the terraces do not grow evenly. Water flow, algae, visitor activity, rainfall, and the management of the springs all influence their shape and color. Some surfaces remain smooth and white, while others darken or become rough. The landscape is natural, yet its modern appearance also depends on careful decisions about where the thermal water is allowed to flow. Far across the ocean, a field of dark boulders lies within a quiet forest in Pennsylvania. At Ringing Rocks Park, certain stones produce clear metallic tones when struck lightly. Other rocks nearby make only dull sounds. The ringing is not caused by hidden metal chambers or artificial construction. Studies suggest that internal stresses within the rock help it vibrate in an unusual way. The exact sound also depends on the stone's shape, size, contact points, and position among neighboring rocks. Removing a boulder or changing how it rests can alter its tone. Geologists understand several parts of the phenomenon, but predicting which stones will ring most clearly remains difficult. A whole field of rocks behaves differently from a single stone examined alone. From this shaded woodland, we travel toward the warm waters of northern Australia. Near the Gulf of Carpentaria, long rolling clouds sometimes appear shortly after dawn. Known as morning glory clouds, they can stretch across a great distance while moving like slow waves through the sky. They often form when sea breezes from different coastlines meet over the Cape York Peninsula. Cooling air, pressure changes, and stable atmospheric layers can create a traveling disturbance. Pilots and local residents have watched these clouds for generations. Their arrival can sometimes be anticipated, but their exact height, length, speed, and timing vary. Researchers understand the broad atmospheric pattern, yet the interaction between coastlines, night cooling, humidity, and wind remains complex enough that not every event can be predicted. Our journey now turns south toward Patagonia. Perito Moreno. Glacier slowly moves from the mountains into a broad blue lake. Unlike many glaciers, it sometimes advances far enough to press against the opposite shore. When this happens, the ice can block part of the lake and separate one arm from the rest. Water rises behind the barrier, placing increasing pressure on the glacier. Eventually, water may carve a tunnel through the ice. The tunnel widens into an arch, which later collapses as the glacier continues to shift. The process is understood, but its schedule is irregular. Ice thickness, snowfall, rainfall, lake level, temperature, and hidden fractures all influence when the next opening may occur. From the cold edge of Patagonia, we drift northeast toward the tropical island of Mauritius. From high above the island's southwestern coast, the ocean seems to pour downward into a vast underwater waterfall. Pale sand forms long streams against the darker blue sea. There is no true drop into a deep ocean abyss. The effect is created by sand and sediment moving from a shallow underwater shelf toward deeper water. Currents, waves, and the steep shape of the seabed produce the striking pattern. Yet the movement changes with storms, tides, and seasonal ocean conditions. Scientists can explain the illusion, but mapping every pathway taken by the shifting sediment requires repeated measurements beneath moving water. Our path continues toward the dry desert of Nevada. Fly geyser rises from the ground in colorful mineral cones, releasing hot water in gentle clouds of steam. Green, orange, red, and brown surfaces surround several small openings. The geyser began after drilling created a pathway for heated groundwater. Dissolved minerals then accumulated around the flowing water, gradually building the unusual formation. Heat-loving microorganisms contribute some of the brighter colors. Their distribution changes with water temperature, chemistry, sunlight, and the age of each mineral surface. The formation is partly accidental and partly natural. Its future shape cannot be predicted precisely because every new layer redirects the water flowing over those beneath it. Our final stop lies beside the Atlantic coast of Senegal. Lake Retba has often appeared pink or reddish, especially when its water becomes highly saline. Salt-tolerant microorganisms produce pigments that help protect them from intense sunlight. The color is not permanent. Rainfall, evaporation, water depth, salt harvesting, and changes in microbial communities can leave the lake pale, gray, or less vividly pink. Researchers understand the organisms involved, but the balance of conditions changes from season to season. A famous color may disappear for a time and return only when the lake's chemistry becomes favorable again. Evening settles over the quiet saltwater, while small ripples soften the reflection of the sky. Beyond the distant shore, more unusual places wait beneath clouds, mountains, forests, and stars. From the pink waters of Senegal, we travel west across the Atlantic and then south along the coast of Peru, toward one of the driest landscapes on Earth. Across the Nazca Desert, long lines, geometric figures, and enormous images of animals have been drawn into the pale ground. Many can only be fully appreciated from high above. The makers remove darker surface stones to reveal lighter soil beneath. The extreme dryness and limited wind help preserve the designs for many centuries. Archaeologists broadly agree that the lines were created by the Nazca culture and related communities. Yet their exact purposes remain debated. Some may have marked ceremonial routes, water sources, sacred places, or relationships with mountains and rainfall. Different figures may have served different purposes rather than belonging to one single plan. From the Peruvian desert, we travel toward the sandstone country of northwestern Saudi Arabia. There, Al-Nasla'a appears as a large boulder divided almost perfectly down the middle. The narrow gap between its two halves looks unusually straight and clean. The rock rests on natural stone supports, while wind and sand have slowly shaped its outer surfaces. Its split most likely follows a fracture already present in the sandstone. Geologists have suggested natural jointing, stress, erosion, or small movements in the ground. Yet the precise sequence that produced such a smooth separation cannot be reconstructed with certainty. The stone has also been marked by people in the past, but there is no reliable evidence that humans cut the entire boulder in half. Our path now leads northwest toward the quiet countryside of Romania. Near the village of Costeti, rounded stones known as trovants rise from sandy ground. Some look like smooth spheres, while others have smaller forms bulging from their surfaces. They are a type of concretion, formed when mineral-rich water cemented grains of sand together inside ancient sediments. After heavy rain, minerals can gather on the outside of exposed stones. This may create thin new layers, encouraging the popular idea that the rocks are slowly growing. They are not alive, and they do not reproduce. Still, researchers continue to study the conditions that created their varied shapes and the internal structures hidden inside them. From these gentle hills, we return to the frozen slopes of Antarctica. Mount Erebus holds one of Earth's few persistent lava lakes. Deep within its crater, molten rock can remain visible for long periods instead of quickly cooling into a solid crust. Gas rising through the magma helps keep the lake moving. Bubbles swell and burst at the surface, sometimes throwing small pieces of lava into the crater. Scientists monitor the volcano with cameras, instruments, and gas measurements. Yet the hidden plumbing system beneath the mountain is difficult to map. Researchers still investigate why some volcanoes maintain long-lived lava lakes, while most do not, and how changes deep below are connected to activity at the surface. Leaving the volcanic ice behind, we travel to the layered cliffs of the Grand Canyon. In several places, very old rocks lie directly beneath much younger layers. Hundreds of millions of years of geological history appear to be missing. This boundary is part of what geologists call the Great Unconformity. It can be found in different forms across several continents. The missing rock may have been removed by erosion, or it may never have been deposited. Ancient uplift, changing seas, glaciers, and the breakup of continents may all have contributed. Researchers continue to debate whether one major global process created much of the gap, or whether different regions lost their rocks at different times. The answer may also help explain changes in ocean chemistry and the environments in which early complex life developed. Across the Pacific, mist settles over the uplands of Laos. The Plain of Jars contains thousands of large stone vessels scattered across fields, hills, and forest edges. Some are taller than a person and weigh several tons. Archaeological evidence connects many of the jars with ancient burial practices. Human remains, ceramic objects, beads, and other materials have been found nearby. Yet questions remain about how the stones were quarried, transported, and arranged across such a wide landscape. The jars may have been part of a larger ceremonial system whose wooden structures and everyday objects have long since disappeared. Local communities have lived beside them for generations, while modern researchers carefully map sites that were once difficult or dangerous to reach. From the highlands of Laos, we travel to the green volcanic island of Dominica. Boiling Lake lies within a flooded volcanic opening surrounded by steep forested slopes. Steam drifts constantly above its gray-blue surface. The water is heated by volcanic gases and hot rock beneath the ground. Temperatures near the edges can approach boiling, while the unstable center is difficult to measure directly. At times, the lake level has suddenly fallen, leaving behind a nearly empty basin. It later refilled as underground water and heat returned. Scientists understand that changes in rainfall, steam pressure, fractures, and geothermal circulation are involved. But the hidden network beneath the lake makes sudden changes difficult to predict. Our final stop lies below the clear waters of the Bahamas. Blue holes descend through limestone platforms into flooded cave systems. From the surface, they appear as dark circles surrounded by much shallower turquoise water. Many formed when sea level was lower and rainwater dissolved the exposed limestone. Later, rising seas flooded the caves and vertical shafts. Some blue holes contain layers of water that barely mix. Deep zones may have little oxygen and can preserve ancient sediments, pollen, animal remains, and chemical records. Divers and robotic instruments have explored only parts of these systems. Narrow passages, unstable rock, darkness, and great depth leave many chambers unmapped. The dark blue opening rests quietly beneath the evening sea. Far below, hidden passages continue through the stone, carrying our journey towards still more places the earth has not fully revealed. Leaving the flooded caves of the Bahamas, we travel northwest toward the open plains of Wyoming, where a solitary stone tower rises above the grasslands. Devils. Tower stands nearly vertical, its sides marked by long columns that look almost carved. It dominates the surrounding landscape, visible from far across the prairie. Geologists agree that the tower formed from magma that cooled beneath the surface. Softer surrounding rock was later removed by erosion, leaving the harder igneous core exposed. Yet its exact origin remains debated. It may have been the neck of a volcano, a shallow intrusion, or a body of magma that never reached the surface. The columns formed as the rock contracted while cooling. Researchers still study how quickly that cooling occurred, and why some columns develop such unusual size and shape. From the dry plains, we cross the Pacific toward the warm islands of Palau. Jellyfish Lake is a marine lake separated from the open ocean by limestone ridges and narrow underground connections. Within it, golden jellyfish drift through green water in enormous numbers. Each day, many of the jellyfish move across the lake, following sunlight that supports microscopic algae living inside their tissues. The migration is well known, but the lake's ecosystem can change suddenly. Jellyfish populations have fallen sharply during periods of unusual heat and later recovered. Scientists continue to study how temperature, rainfall, salinity, food supply, and hidden seawater exchange influence the lake. Its isolation is real, but it is not complete. Our journey now turns south toward the coldest desert on Earth. The McMurdo dry valleys of Antarctica contain broad areas almost free of snow and ice. Dark mountains, frozen lakes, dry soil, and strong winds create a landscape unlike most of the continent. The valleys remain dry because nearby mountains block much of the snowfall. Cold, dense winds also descend from the high ice sheet, removing loose snow and moisture. Even here, microscopic life survives in rocks, soils, and salty water beneath ice. Some organisms remain inactive for long periods and become active when brief moisture appears. Researchers are still mapping hidden brines beneath the valleys. They want to understand how water moves through frozen ground and how life persists near the limits of temperature and dryness. From Antarctica, we travel north to the Atlantic edge of the Namib Desert. Along the skeleton coast, enormous dunes meet cold ocean water beneath frequent fog. Rain is rare, yet moisture from the sea reaches far inland. Beetles, spiders, lichens, and desert plants collect droplets from the moving fog. Some animals lift their bodies into the wind, allowing water to condense and run toward their mouths. Scientists understand the basic source of the fog, produced when moist air passes over the cold Benguela Current. Yet its inland movement changes with wind, temperature, dunes, and coastal conditions. Researchers continue to investigate how much water the fog provides and how future ocean warming may alter this narrow but important source of life. We now cross another ocean and arrive in the quiet Badlands of New Mexico, in the Bisti and Denazin wilderness. Soft hills are crowned by balanced rocks, mushroom-shaped hoodoos, and pale stone wings. The formations appear scattered without any simple pattern. They were shaped by differential erosion. Harder layers protected softer sediment beneath them, while wind, rain, freezing, and flowing water slowly remove the surrounding ground. The process is clear, but each formation follows its own history. A small crack or mineral difference can decide whether a tower survives for centuries or collapses after a single storm. The landscape continues to change too slowly for a visitor to notice, yet quickly enough that photographs taken decades apart can reveal missing stones and altered shapes. From these dry badlands, we travel south along the Andes to the high plateau of northern Chile. At El Tatio, steam rises from geysers, hot pools, and narrow vents before sunrise. The cold air makes every plume appear larger and softer. Water descends through cracks, is heated by volcanic rock, and returns under pressure. But the underground plumbing is complex and constantly changing. A small shift in a fracture can weaken one geyser and strengthen another. Earthquakes, mineral deposits, rainfall, and human activity may all redirect the hidden flow. Scientists can measure temperature and chemistry at the surface, yet much of the system remains beyond direct observation beneath the plateau. Our path now turns north toward the Great Salt Lake in Utah. The lake has no outlet to the sea, so minerals remain behind as water evaporates. Its salinity changes greatly from one region and season to another. Along some shores, microbial communities build layered structures called microbialites. These living mats resemble forms that were common in ancient oceans. Researchers study how bacteria, algae, minerals, sunlight, and water chemistry work together to create them. The broad process is understood, but growth rates and seasonal changes vary. Falling water levels can expose the structures to air, while rising salinity can alter the organisms that live around them. The lake's rapid changes are creating new questions faster than some can be answered. Our final stop lies near the northern Ural Mountains of Russia. The Man-Pupuna rock pillars rise alone above a remote plateau. Their narrow towers stand where a mountain ridge once extended across the landscape. Weathering removed the weaker rock, leaving harder columns behind. Frost, wind, rain, and repeated temperature changes slowly shape their steep sides. Geologists understand this general history, but the exact structure of the original ridge is gone. Each pillar preserves only part of a much larger landscape that no longer exists. Clouds drift between the stone towers as evening settles over the plateau. Beyond them, more quiet places wait, shaped by pressure, weather, water, and the long patience of the earth. Leaving the stone pillars of the Ural Mountains, we travel westward across the ocean toward the thermal landscape of Yellowstone. Grand Prismatic Spring appears as a deep blue pool surrounded by broad rings of green, yellow, orange, and rust. Steam moves slowly across its surface, sometimes hiding the colors before revealing them again. The blue center is created by the way clear, deep water absorbs and scatters light. Around the cooler edges, heat-loving microorganisms form colored communities adapted to different temperatures. Scientists understand the main source of the colors, but the spring is not a fixed painting. Water flow, temperature, chemistry, sunlight, and microbial competition continually alter the width and brightness of each band. The underground channels feeding the spring are difficult to observe directly. Small changes beneath the surface may shift the visible colors long before researchers understand what has changed below. From warm water and rising steam, we travel east toward Egypt's western desert. In the White Desert, pale chalk formations rise from the sand like mushrooms, towers, animals, and pieces of frozen cloud. Their smooth shapes seem almost too delicate for such an open landscape. The chalk was deposited when this region lay beneath an ancient sea. Over time, uplift exposed the soft rock to wind-blown sand, rare rain, and changing temperatures. The broad process is clear, yet each formation develops differently. Tiny variations in hardness, fractures, moisture, and wind direction decide which parts disappear and which remain standing. Some shapes may survive for centuries, while a single unusual storm can weaken a narrow base. The desert is constantly sculpting itself, though most of its work is too slow and quiet to notice. Our journey now crosses Asia toward the misty mountains of central China. At Zhangjiaye, thousands of narrow sandstone pillars rise above forested valleys. Clouds often gather between them, making the highest columns appear to float. The pillars formed as water entered fractures in thick layers of quartz-rich sandstone. Weathering widened the cracks, while streams and erosion removed the softer material between them. Plants also influenced the landscape. Roots opened small fractures, while soil and vegetation protected other surfaces from rapid erosion. Researchers understand these processes, but the extraordinary density and height of the pillars depend on a complex geological history. Uplift, rainfall, rock strength, and the direction of fractures all contributed over immense periods. From the clouded mountains, we descend into a vast opening in the forests of Mexico. The Cave of Swallows is a deep vertical shaft with steep limestone walls. At dawn and evening, large groups of birds may circle through the entrance before disappearing into the darkness below. Despite its name, many of the birds are swifts and parakeets rather than true swallows. They use ledges and cavities in the rock for shelter and nesting. The cave formed as water-dissolved limestone along fractures, gradually enlarging an underground chamber. Parts of the roof later collapsed, opening the enormous shaft to the sky. Its origin is broadly understood, but the full system of hidden passages beneath the floor remains difficult to map. Water continues to move through the rock, altering spaces that humans may never directly enter. We travel next toward the dry hills near the Caspian Sea. Azerbaijan contains hundreds of mud volcanoes. Some form low cones and quiet pools, while others release bubbles of gas and send cool gray mud slowly down their slopes. They are not usually powered by molten rock. Instead, pressurized water, clay, and natural gas rise through thick layers of sediment. Researchers study them because they reveal information about fluids and hydrocarbons deep below the surface. Yet their eruptions can be difficult to predict. Pressure may build for years before suddenly finding a new path upward. Earthquakes, shifting fractures, and changes in underground gas movement may influence when an event becomes active. From these dry mud fields, we return to the cold interior of Antarctica. Lake Untersee lies beneath a permanent cover of ice, surrounded by mountains and glaciers. Its water is extremely clear, cold, and poor in nutrients. On the lake floor, microbial communities build unusual cone-shaped structures. These resemble ancient stromatolites formed by microorganisms in much earlier chapters of Earth's history. Scientists study the lake as a possible comparison for cold environments on other worlds. Yet many questions remain about how its microbes obtain enough energy and how slowly the underwater structures grow. The lake also contains unusual zones of dissolved gas and very alkaline water. Its isolation, chemistry, and long periods of darkness create conditions that are still being carefully examined. Leaving the ice behind, we move toward the warm limestone coast of Oman. The Bima sinkhole appears as a circular opening filled with blue-green water. Stone walls descend toward the pool, while the nearby sea lies only a short distance away. The sinkhole probably formed when limestone dissolved and an underground cavity collapsed. Its water appears to include both fresh groundwater and seawater entering through hidden cracks. The general explanation is simple, but the exact underground connection has not been fully mapped. Tides, rainfall, and seasonal groundwater levels may all influence the pool. Local stories once imagined that a falling star created the opening. The geological explanation is more likely, though the unseen water routes beneath it still preserve part of the mystery. Our final stop for this part of the journey lies among the valleys of central Turkey. Cappadocia is filled with tall stone cones known as fairy chimneys. Some carry harder caps of rock, while others have been carved into homes, storerooms, chapels, and shelters. The landscape began with thick deposits of volcanic ash. These deposits hardened into soft rock called tuff, later covered in places by more resistant lava. Rain and wind removed the softer material, while harder caps protected the columns beneath them. Yet the exact pace of erosion varies greatly across short distances. Human activity added another layer to the landscape. Cutting rooms into the rock may strengthen some sections while weakening others, changing how water and temperature affect the stone. Evening light settles across the valleys, turning the pale formation soft shades of rose and gray. Beyond these quiet volcanic hills, our journey continues toward more hidden lakes, strange coastlines, ancient craters, and landscapes still changing beneath the night sky. Leaving the pale valleys of Cappadocia behind, we travel eastward toward the dry foothills of southeastern Kazakhstan. Within Altan, Emel National Park, a long ridge of sand rises above the open plain. Under certain conditions, the dune produces a deep humming sound that can travel across the quiet landscape. The sound begins when dry grains slide together in a moving layer. Their size, shape, moisture, and arrangement allow many grains to vibrate at nearly the same frequency. Scientists understand this broad process, but singing dunes do not always sing. A dune may remain silent after rain, during cold weather, or when its surface has been disturbed. Researchers still study how millions of grains synchronize their movement, and why some dunes produce a low hum, while others create higher notes, short pulses, or no sound at all. From the warm sand, we rise into the thin, cold air of the Andes. On high mountain slopes, fields of narrow snow blades point toward the sun. These formations are called penitentes, and some grow taller than a person. They begin when intense sunlight turns snow directly into water vapor. Small hollows receive more reflected energy than surrounding ridges, causing them to deepen while shaded peaks remain. The general mechanism is known, yet their spacing and final height are difficult to predict. Humidity, wind, sunlight, dust, temperature, and the structure of the snow all influence their growth, because similar shapes may exist on icy worlds beyond Earth. Scientists study these quiet forests of snow to better understand distant landscapes that no person has yet visited. We now travel west toward the mountains of northern Iran. Adbadab. Surt, mineral-rich spring water descends across a hillside in a series of orange, gold, cream, and rust-colored terraces. The warm water rises through layers of rock carrying dissolved calcium and iron. As it reaches the surface, minerals settle and slowly build the curved pools. Scientists understand how the terraces grow, but their development is delicate. A slight change in water flow can dry one pool, flood another, or redirect mineral deposits across a new path. The colors also change with iron content, microorganisms, moisture, and sunlight. The hillside is therefore not a finished structure, but a slow record of water continually choosing new routes. From these quiet springs, we cross the Indian Ocean toward the islands of Vanuatu. Mount Yasser rises above the forests of Tanna Island and has remained frequently active for a very long time. At night, glowing fragments of lava can sometimes be seen rising above its crater. Gas bubbles travel upward through the magma and burst near the surface, producing repeated explosions. The activity is often described as Strombolian, after another volcano far away in the Mediterranean. Although the basic process is familiar, Yasser's long persistence remains scientifically valuable. Researchers continue to study the size of its magma reservoir, the pathways taken by gas, and the reasons its activity changes from one day to another. Local communities have lived within sight and sound of the volcano for generations. The mountain is both a geological system and a familiar presence within daily life. Northwest of Vanuatu, another volcanic landscape rests within a lake in the Philippines. Taal is a complex volcano surrounded by water, with several craters, vents, islands, and older volcanic structures nested within one another. Its shape was produced by many eruptions rather than one simple event. Large ancient eruptions formed a broad depression that later filled with water, while newer activity built features inside it. Scientists monitor earthquakes, gas, ground movement, and lake chemistry. Yet volcanic fluids can move through hidden fractures, and changes beneath one area may influence vents somewhere else. The volcano's structure makes forecasting difficult. Its quiet surface may conceal movements occurring far below the lake and surrounding towns. From this restless landscape, we continue north toward the wetlands of northeastern China. Near Panjin, broad coastal marshes turn a deep red during part of the year. The color comes from a salt-tolerant plant commonly known as seepweed. Young plants begin green and gradually become red as the season advances. Salinity, water depth, temperature, and soil conditions affect the timing and intensity of the color. The marsh lies where river sediment, seawater, and human land use meet. Channels shift, new mudflats form, and older wetlands may become drier or more deeply flooded. Researchers understand the plant's biology, but predicting the future of the red landscape is more difficult. Coastal development, changing river flow, sea level rise, and migratory birds all interact within the same fragile system. Our journey now crosses the Pacific and the Atlantic, arriving on the island of Trinidad. Pitch Lake appears as a broad, dark surface of natural asphalt. Some areas are firm enough to walk across, while others soften, bubble, or release water and gas. The material rises from petroleum deposits below, where lighter components gradually escape and leave heavier bitumen behind. Small islands of vegetation can form on parts of the surface. Microorganisms have also been found within tiny water droplets trapped inside the asphalt. Scientists continue to study how fluids move through the lake and how organisms survive in such an unusual chemical environment. The surface changes slowly, opening cracks and closing them again like a landscape that never becomes entirely solid. For our final destination, we travel to the forested hills of Ghana. Lake Bosumtwi fills a circular basin formed by a meteorite impact more than 1 million years ago. Rain and small streams feed the lake, but no large river flows outward from it. Sediments have gathered on the lake floor in thin layers, preserving records of rainfall, vegetation, fires, and climate across long periods. Researchers use these layers to reconstruct changes in West Africa's past. Yet each layer must be interpreted carefully, because wind, erosion, microorganisms, and movement within the lake can alter the record. The crater's origin is known, but the history written in its water and mud is still being read, one sample at a time. And now, as night settles over the circular lake, our long journey begins to slow. We have crossed deserts where stones move, forests where trunks bend, lakes hidden beneath ice, caves filled with light, and islands still learning how to become living worlds. Some mysteries became smaller when measured carefully. Others opened into deeper questions about time, climate, stone, water, and life. There is no need to hold on to every name or explanation. Let the distant landscape soften and drift away. Imagine the earth turning quietly beneath the stars, carrying every mountain, river, forest, and sleeping shoreline through the darkness. The wind moves gently across the sand. A small wave reaches an empty beach. Snow settles on a distant ridge, and somewhere beneath the ground, water continues along a hidden path, slowly shaping a place that future travelers may one day understand a little more clearly. For now, the world can remain quiet. The questions can wait until morning, and you can rest